I have very much pleasure in declaring the XPT train the winning entry for the 1981 Australian Transport Industry Award. Congratulations.
Thank you very much.
Behind this event lies some 2 years of the most intensive rail vehicle design, development and construction ever undertaken in this country.
It marks the beginning of a new era, not only in railways, but engineering technology in connection with railways in this country. I want to congratulate Comeng on a fine job. I want to congratulate the men and women who built and outfitted the train. And I'll tell you, boys, there's plenty more where this came from.
The first XPT entered commercial service in New South Wales on the 8th of April 1982, just 2.5 years after Commonwealth Engineering were asked to develop their proposal for an alternative to 11 different design types required by the State Rail Authority. The XPT is accepted as being the most significant development in Australian intercity passenger train design in the past 30 years, providing a standard equal to the very best of overseas rail systems. The stainless steel passenger cars are fully air-conditioned with wide panoramic windows of specially treated glass that reject 75% of the sun's heat. Numerous options are available through the use of a modular design throughout the train. In New South Wales, a buffet car provides meals at a servery counter for the passengers to carry back to their seats. But the wide automatic doors, interconnecting vestibules and roomy corridors allow the option of airline-type trolleys, so stewards could serve meals at the passengers' seats. The deeply upholstered reclining seats are ideally suited to long journeys, while the airbag suspension means there's little vibration transferred from the track. The XPT was designed to suit existing track conditions in Australia. In New South Wales, the mountains and numerous curves made design of a high-performance train particularly difficult. Here, there are some of the longest and steepest mainline grades in the world. A very high power-to-weight ratio was required for fast acceleration through the hills. But this meant that rapid, efficient, and reliable braking was of equal importance. Much of Australia's track, particularly in New South Wales, dates back to the early days. So design of the suspension system and bogies provided other unique problems. Considerable movement, both vertically and laterally, had to be built into the suspension, much greater than for any overseas train, so that the passengers would not be aware of the lumps and bumps in the track. Much has been said about the XPT being a copy of the British HST. But while the general design concept is based on the HST under a Comeng license agreement with British Rail, there's a great deal of difference between the two trains. The British mainline track is carpet smooth in comparison, with gentle curves and lower gradients. Thus, the British HST can maintain top speeds on their mainline system of 125 miles an hour, or 200 kilometres, without any damage to the track or discomfort for the passengers. But the HST, if transported complete to Sydney, would never get over the first gradient, let alone stay on our meandering track.
Well, it's a great concept, Sid, but we've got a lot of work to do before we can get to work in Australia.
Yes, there's certainly a lot of redesign work to do to begin with. We've got to rework the suspension units, we've got to re-gear it to handle your gradients, we've got the engine to derate, and we've got a very much larger cooler group to fit in.
And of course your whole structure's larger anyway.
Basically, it's a complete redesign around that original concept.
No, very much so.
The decision to use the HST concept was made in 1979. Then, in close association with British Rail through their subsidiary Transmark, a complete redesign began at Commonwealth Engineering's Granville headquarters. The latest computer technology available at Comeng meant that they were able to reduce the design time to months rather than years. But in train design, there's much that only the human touch can achieve, and many hundreds of man-hours were used in producing sketches, layouts and models. In some cases, these were taken to full-size mock-up stage, so that the designers and engineers were able to check the practical applications before proceeding further.
This is the centre panel, just remembering that this is all black and with white lettering on each of the gauges and dials, so that the pressure gauges, the load meter.
Particular emphasis was placed on the cabin and on the design of the bogies. Both were to set entirely new standards in Australia, so engineers and unions had to be satisfied. Two prototype bogies were designed and tested exhaustively on New South Wales tracks. These were the result of prolonged computer analysis of existing track conditions. Dummy passenger loads were carried over the bogies at speeds up to 140 kilometres an hour. The ride in the locomotive and in the standard instrument car provided a sharp contrast to the smoothness of the passenger car under test. The ride index figures were comparable to an average European train on their very best track. Even the techniques used in the construction of the power car broke new ground in Australia. For instance, the underframe consists of a series of individual segments, each of which is fully welded, X-rayed and machined prior to being assembled in the main construction jig. This method minimises weld distortions in the completed structure, and overall critical dimensions are maintained within close tolerances. It also allowed great weight saving, a critical factor in the design of a high-performance train. The side frames were also prefabricated in jigs, again resulting in weight reduction and close tolerances. These completed frames were simply stood up on the underframe, interconnected and welded into position. Comeng had originally intended the power car to be in stainless steel, but the customer decided upon the heavier carbon steel. Even so, a special welding technique still resulted in a perfectly smooth surface.
Now the whole of this cab is fiberglass, including the front nose and the doors, the panels here.
Yeah. And this fiberglass is resistant to impacts from things from the track, bricks and things like that?
Yes, we've done tests, impact tests up to 200 kilometres an hour, both on the nose and on the main shell.
Construction of the fiberglass cabin required a number of individually complex stages. From the original drawings, a full-size wooden pattern was built, coated with resin and polished to a high sheen. Onto this pattern was built one of the most complex fiberglass moulds ever accomplished in this country. Built in 4 separate sections, the mould was then bolted together in a special rotating jig, so that the laminate could always be laid down hand. The result is a main shell, approximately 50 millimetres thick, moulded all in one piece for greater strength. The shell has both an inner and outer gel coat skin and incorporates all necessary conduits, pipes and mounting plates ready for fitting out. The nose is a separate unit, a good example of the modular design used throughout the train. The XPT engine is a Paxman Valenta 12-cylinder turbocharged diesel unit rated at 1,492 kilowatts, directly coupled to the brush alternators. This is basically the same engine and alternator set as used in the British HST, but the engine has been derated to suit our altitudes and ambient temperatures. Despite its size, there's still room for crew members to pass or gain access for maintenance. The engine cooling group, or radiator to the layman, is constructed entirely from aluminium, again as a means of weight reduction. Obviously, because of our ambient temperatures, this is some twice the size of the HST version and has been specially designed for Australian conditions. It's a complete module which can be removed without disturbing any other engine components. The same applies to the main electrical module supplied by Brush. Hatches in the roof of the power car allow easy replacement of any of the components, so that downtime is kept to a minimum when major services are required. This modular concept is carried through to the smaller components for ease of routine maintenance. Electrical wiring throughout the train is to a numbered code with the identifying number printed on each individual cable at regular intervals. At any part of the train, the required cable can be identified and traced. Power throughout the train for lighting, cooking and air conditioning comes from an auxiliary alternator coupled to the main traction alternator. With 2 power cars to each train, there's ample for all needs. This eliminates the auxiliary power car, common to most country trains, another major weight saving. The driver's superb impact-resistant laminated windscreen is 25 millimeters thick and contains its own heating unit for clear visibility at all times. The completed cabin, with all its controls, electrical wiring and air hoses already fitted, is simply lifted into position and connected. There's a massive steel collision post to protect the crew. This is covered by the detachable nose.
Drop it down right here, right?
The exterior styling, aesthetics and colour scheme of the XPT were the result of considerable development and study. The aim was to create a visual impact so good-looking that people would want to travel on it once they'd seen it pass by. But to keep passengers coming back for more, the ride had to be far better than they'd ever experienced before. Comeng knew that their own bogie design would achieve this, but the customer selected the existing British design, which required considerable modification to suit our poorer track conditions. Commonwealth Engineering manufactures these bogies at their Mittagong factory, and though the modifications have resulted in very good ride characteristics, are continuing to develop their own lighter and less complex design. One thing common to both bogie designs is the braking system. Rapid acceleration requires equally rapid braking, so huge discs are fitted to both sides of each wheel. Almost the whole of the wheel area is used for braking, providing a margin of safety equal to or better than anywhere else in the world. To maintain traction at all times, even under emergency braking conditions, all axles are fitted with wheel slip detectors, which sense and correct the onset of slip automatically and individually on each axle. The traction motors, one on each axle, are mounted on the bogie frame so as to minimize the unsprung mass. Drive is through a flexible coupling and gearbox. Nothing was left to chance. The braking required for such power was thoroughly tested on one of the world's most powerful dynamometer rigs. This machine can simulate a mass of up to 32 tons per wheel at speeds up to 250 kilometers an hour. The first bogies were rolled under an XPT power car in June 1981, just under 2 years after work commenced on the design. The power car bogies are of the fabricated type, using steel coil springs in conjunction with Alston links. At 72 tons mass, the XPT power cars are among the lightest 1500 kilowatt or 2000 horsepower diesel-electric locomotives in the world. By contrast, existing locomotives of the same power in New South Wales weigh in at 121 tons. These are the first purpose-built passenger locomotives constructed for the New South Wales rail system since the days of steam. Before the completed power car is tested on the track, static load testing is conducted in Comeng's own test facility. The alternator is disconnected from the traction motors and hooked up to a huge electric heating unit, similar to a giant electric kettle. This dummy load allows engineers to verify the electrical output and check for any faults. An array of test instruments monitors all functions of the power car as the engineer controls the powerful Paxman diesel by remote control. Detailed readings are taken for each of the 5 throttle settings, with the engine revolutions and electrical output checked against the design parameters. It's a complex but very effective way to boil the kettle. With static testing complete, it's out onto the main track for acceptance trials. Australian trained designers have no dedicated test track, so they have the unenviable task of carrying out their final tests and adjustments on the customer's main line, with the customer and public watching over their shoulders. But the XPT came through with flying colours, with the test results fully meeting the customer's expectations. The special suspension provided the best ride yet on New South Wales tracks. The passenger cars provide a new level of comfort. Quiet, cool and glare-free, yet still providing an uninterrupted view of the passing countryside. Every detail had been closely studied to provide a perfect combination of strength, weight reduction and passenger comfort. The passenger cars are constructed entirely of stainless steel, with the exception of the bolster headstock units. The close centres of the U-beam cross members provide underfloor strength and rigidity without the weight of the traditional carbon steel frames. All pipes and conduits are fitted under the floor before the frame is inverted, and the wall frames and stainless steel skin are fitted. The vehicles are 24.2 metres in length, the longest such saloon-type coaches in New South Wales. The walls and roof are both prefabricated, with the skin spot welded to the frames. Thanks to the inherent strength of the stainless steel combined with the light weight, they are then simply lifted into position and welded in place. This modular technique, used throughout the XPT, not only allowed each section to work independently without interruption, it also guaranteed close tolerances through the use of permanent jigs. All materials used throughout the train are fire retardant, even the insulation in the body cavities, carpet and seat covers. The complete insulation of the shell performs a dual role, not only aiding the air conditioning, but also dampening the sound from the track. Each car has its own air conditioning unit, a twin split system with 2 evaporators in the ceiling and 2 compressor condenser units on the frame under the floor. Even if one unit was to fail, it wouldn't mean the complete loss of air conditioning in the car. All cars are basically identical, again following the modular concept. Only the interior fittings and layouts vary according to their function. Originally, the XPT had been designed as a two-class train, but later the customer changed the order to single-class. Because of the common frame and shell, this didn't present too many difficulties, and Comeng can still produce alternative cars from the original drawings if required. All luggage racks, internal linings and lighting units are in 2-metre modules, matching the window spacing. Fiberglass is used extensively throughout the car for a bright, smooth outline and ease of cleaning. The XPT seat design is new to Australia and allows the car capacity to be increased from 60 to 70 passengers without loss of legroom. The automatic doors are activated by pressure-sensitive pads under the floor covering. The guard's compartment is fully equipped with toilet and galley facilities, and a retractable mirror allows him to view the full length of the train.
Hello, Dave. I've come through the train now and...
The intercom can also be used as a public address system, broadcasting to all cars at the touch of a button. In April 1982, the first paying passengers sampled the XPT between Sydney and Dubbo, 400 kilometres to the west. Since then, as passengers responded and more train sets were completed, daily services were extended to the main northern and southern lines. The XPT was intended as an alternative to air travel on medium to long distance routes. The general cruising speed of 160 kilometres an hour and the fast acceleration mean that passengers now have a day train, whereas before they had to choose between an overnight sleeper or air travel. Passenger comfort, safety, reliability and a high cruising speed have all contributed to the success of the XPT. But it was the foresight, design expertise and construction techniques of Commonwealth engineering that made this dream a reality.